In this video, I introduce a contrastive loss for self-supervised learning. Contrastive learning maximizes mutual information between different views of the same image. Given a set of views, visual representations are learned by encoding views of the same image close to each other in an embedding space, while pushing views of different images apart. Self-supervised learning uses the contrastive loss to learn visual representations without requiring human annotations. As shown here, these are matching views. Their representations in the embedding space are close to each other. This is the matching view. His representation is far away from those points. In contrary, the traditional predictive learning learns transformation from V1 to V2 via embedding Z, as shown here. Maximizing the joint probability of a pixel in an image trains the transformation model to generate high-quality representations. Contrastive loss is applied to train self-supervised learning models to learn embedding that contrasts samples from two different distributions. A dataset of V1 and V2 consists of congruent and incongruent pairs V1L and V2L, namely positive pairs X and negative pairs Y. A discriminating function h theta is trained to achieve high values for positive pairs and low values for negative pairs, namely correctly select a single positive sample X out of a set S to maximize the loss defined as here and explained in this figure. This input image V1 and this input image V2 is an encoder, and we use contrastive loss in embedding space to train the model. To construct S, we need to fix a view and enumerate the positives and negatives from other views. The contrastive objective is rewritten as here. The numerator is a likelihood, h theta is prior. The denominator is a marginal probability. Noise contrastive estimation approximates the n-way softmax cross entropy for the contrastive loss computation. Given an anchor V1I sampled from V1 is the best match, V2 sampled from V2, and the probability is computed by using this formulation. Directly computing the denominator is expensive. NCE uses an normalized statistic model to compute P by fitting density P to data distribution PD via binary classifier H theta to distinguish the real data from noise samples in a distribution Pn. Namely, a binary classifier is trained to find posterior probability P given V1I. Suppose that the noise distribution Pn is a uniform distribution over V2, namely Pn is equal to 1 over n. If m noise samples are sampled to pair with each data sample, the posterior probability that a given V2 comes from the data distribution is computed by using this formulation. The NCE objective is obtained by minimizing the negative log posterior probability of the correct labels D over data and noise samples, as shown here, where B caret is empirical data distribution, as shown here. V1I sampled from P caret. Given V1I, P2 sampled from P caret with D equal to 1 in data distribution. And given V1I, V2 sampled from Pn with D0 in noise distribution Pn. For more details, please check with these references. Thank you. Bye.